Hi everyone, and welcome back to Education with Eleanor. Today we're doing an example on magnetic flux, which is also a subject in magnetic fields. And if you like this content, press the thumbs up button and subscribe for more videos on physics, mathematics and science. The first thing we need to understand is, what is flux? So if we have an area, and this is a loop, as in it's a loop that could be conducting wire. It could not be conducting wire, conducting current, but the first thing is, flux is the amount of a substance going through a unit area. So this rectangle is on its side, and because it has area, if the magnetic field is going through it like this, then we have a magnetic field going through it. Therefore, we have a magnetic field going through a certain area, and so we will have a magnetic flux. So that's a very important consideration when we're doing this. I'm just going to turn off the grid lines on this page because we don't need them. And that's an important aspect of this. The question is, how do we calculate the magnetic flux? So on the right hand side here, we've got a whole bunch of theory that you can screenshot, but I'm just going to go through it and get straight into the questions, and you'll understand the theory as we go. So to calculate the magnetic flux in part A, it's given by the magnetic field strength when it is at right angles to the given area, multiplied by the cosine of the angle that is in between the normal to the area and the magnetic field. So if you're wondering, what in the world does that all mean? Well, back to our diagram at the start. First of all, let's establish the normal to the area. The normal to the area will be at 90 degrees to the area. So if we drew a normal line, okay, that will be 90 degrees to the area. And then if we look at the magnetic field, which is also going horizontally in this case, so if we look at that magnetic field here, we can see that this line is actually parallel to the normal. So if it's parallel to the normal, in this case, we have an angle of 0 degrees between the normal and the magnetic field. The next thing that you need to understand is that when this is happening, we can also see that the magnetic field and the area, which is here, given by this, if we look at that, then the magnetic field and the area are at 90 degrees. So when the magnetic field is 90 degrees to the area, you are going to get the full amount of magnetic flux going through the area, and the cosine of the 0 degrees is equal to 1. And that's very important to understand. So you're wondering, oh, what does this all mean? So the magnetic flux, like we said before, is the magnetic field strength when it's at right angles to the area multiplied by cosine theta. Now, if cosine theta is 1, because theta is at 0 degrees, then whatever the field strength is multiplied by the area, this will be the full magnetic flux. So that's how that works. Now, if we're looking at when the magnetic field and the area are not parallel to, they are parallel to each other. So let's draw that. So if we have an area like this, and the magnetic field is parallel to it. So let's draw the normal. The normal to the magnetic field is at right angles. So what's going to happen is, if you actually look at the angle between the magnetic field and the normal, it's 90 degrees, and that's when we're going to have cosine of 90 degrees. Cosine of 90 degrees is 0, and so therefore you get no magnetic flux. Let's practice this. So we have in part A circle, and it's flat on the screen, and then the magnetic field is coming out of the page. As a result of that, the magnetic field and the circle, the area, they're at 90 degrees to each other. And if we know it's 90 degrees to each other, we know that the angle theta is 0 degrees, because the normal to the area and the normal to the area will also be coming out of the page or into the page, and that's going to be parallel to the magnetic field. So we know that the magnetic field strength is 0.15 Tesla, and to get the area, we need to do pi r squared. So before we even calculate anything, let's do our area. So our area is given by pi r squared because this is a circle. R being the radius. So pi is multiplied by, now the radius is 20 centimeters, that's not SI units. So when we have 20 centimeters, we need to change it back to meters. So that'll be times 10 to the negative 2, and that'll get you back to meters. And we need to divide this by 2 because we need the radius. 20 centimeters is the diameter. So the answer to this is, and don't forget to square our radius. So our final answer for this is, for just the area, will be 0.01 pi meters. Now this is an exact answer. I'm leaving it like that because we need to substitute it into our magnetic flux equation. So it'll be the strength of the magnetic field multiplied by the area multiplied by cosine theta. The magnetic field strength was 0.15 Tesla multiplied by our area of 0.01 pi meters squared, and then multiplied by cosine of 0 degrees. So this will equal 4.7 times 10 to the negative 3 times 1. So the cosine of 0 is equal to 1. So our magnetic field is magnetic flux is 4.7 times 10 to the negative 3 Webers. And that's a W with a little b. Let's move on, part B. And let's copy this question. So in this question, we're going to look at calculating the magnetic flux going through a rectangular loop. Now, first of all, you need the area, and the area will be the length times the width. And the length is 6 centimeters. Now, 6 centimeters is not SI units. So to change that to meters, you can also multiply it by 10 to the negative 2 or divide it by 100. That's the same thing. So that'll be meters multiplied by 4 centimeters, which is the same as 4 times 10 to the negative 2 meters. And so our area is 2.4 times 10 to the negative 3 meters squared. Now we can calculate our magnetic flux. The first thing we need to look at is it perpendicular? Like is the area of that it's going through and the magnetic field, are they perpendicular to each other? Now, if we think about it, if this is our piece of paper, like we're looking at it from the side, and our loop is actually turned on the side like this, the magnetic field is going into the paper, so, or inside the screen, or inside your notebook. As we can see here, they're at right angles and to each other. Or if we look at the normal to the area, so the normal to the area is like this, and we can see that the magnetic field and the normal to the area is parallel, so they're 0 degrees. Here's the angle. So we will have the maximum magnetic flux, so we need to do the magnetic field strength multiplied by the area multiplied by cosine of theta. So we have 0.020 Tesla multiplied by 2.4 times 10 to the negative 3 meters squared multiplied by cosine of 0 degrees. And this will equal 4.8 times 10 to the negative 4 Webers. Let's do the next question. And we'll copy the question. There we go. All right. In this question, we're looking at what is the magnetic flux. Now, before we do anything else, we need to find out, is the magnetic field and the area, are they perpendicular to each other or parallel? Now, what's happening here is, or the way that it's drawn, is your magnetic field is going to the left, and the area is actually also going horizontally to that as well, so parallel to it like this. Okay, now let's draw the normal to the area, which will look like this, and that's at 90 degrees to the area. So what is the angle between the magnetic field and the normal? In this case, it's 90 degrees, so theta equals 90 degrees, or the magnetic field, B, is parallel to the area. Now, why do we care about this? Remember that your magnetic flux is the field strength multiplied by the area times cosine theta. And in this case, when we look at cosine theta, we've got an angle of 90 degrees. So cosine of theta is cosine of 90 degrees, and from before we learnt that cosine of 90 degrees is actually 0. So as a result of that, our magnetic flux is 0 Webers. And it's because the magnetic field is parallel to the area, or the angle between the normal and the magnetic field is 90 degrees. Alright, I hope you've learnt a lot from this particular little lesson, and if you liked it, press the thumbs up button and subscribe for more videos on physics, mathematics and science. Remember to hit the notification bell as well. Alright, see you next time. Bye!